I'm going to try to start simple and work my way up as we look at these, and we're just going to say, when do we have to get fancier and when can we stick with 2 dimensions in writing out these structures? And what I'm going to use for these purposes is just a generic atom. So I'm just going to draw a circle. This is some generic atom. I don't want there to be any implication that that's oxygen. It's just a circle. And you'll see as we go, the more atoms you have, the more circles I'm going to connect. If you need to draw just one atom, I think that's okay. We don't even need to give it more detail than that, and you won't have to get any fancier because it's not going to be out of plane for any reason. If you have 2 atoms attached to each other, something like that, that will fit in one plane every single time, so we don't need to do anything fancy, and I don't think anybody would screw it up. So and by the way, this is a line, but for example, if you had diatomic hydrogen, you'd just write H, H, and be done with it, right? The Lewis structure would match exactly how things are arranged in 3-dimensional space. Things start to get more exciting once you start having more atoms involved. So if you have 3 atoms involved, and no other non-bonding pairs, then we end up with a situation like this. Here's our central atom, and I'm going to attach another atom, and then I'm going to attach another atom. And I think most of you would be upset if I put it there, or there, or there, or there, because you intuitively want to see it 180 degrees apart, because 180 degrees apart is the farthest you can get 2 things. And I realize that's not perfect 180, but you get the idea. So 180 degrees right there. And so if we look at that, I think it's worth it as we go here. We can put in a bond angle. We've got 180 degrees. Try and get 2 things farther apart than 180 degrees around a central point, and you won't. All right, so examples of that. We saw previously something like CO2. And then one thing to note right now is we only have 2 things attached to our central atom, and there are no non-bonding pairs, and that's going to add a level of difficulty for us in a bit. And you can take one of these off and replace it with a non-bonding pair. I'll just mention that. You could have like a non-bonding pair there, and then you'd have whatever that ends up being, that compound, something like draw some bonds in there, and you have carbon monoxide, but that ends up 2, which is a straight line, and you can fit it on one page pretty easily, right? One plane. Once we get to 3 things attached to our central atoms, then we'll have to watch out. So I'm going to draw my central atom, and I'm going to draw 3 things attached to it. And actually, still on the screen over here, you can see that BH3. I think it's intuitive for you to spread things as far apart as possible, which, when you have 3 things around a central point, is going to be about 120 degrees. You don't need to draw that in or out of the plane of the page, because those 4 points are in one plane. If you only have 3 things around a central point, you can get that all in one plane. Now, we can modify it a little bit. What if, right, we take one of our atoms and replace it with a non-bonding pair? So we have something like that. What happens is not that this snaps to linear. This keeps this geometry, but up here now we just don't have an atom attached. So you might see something like our bond to those 2, and then a non-bonding pair right there. And what happens is that this bond angle decreases a little bit, less than 120 degrees. And I do want to point out, as we're going through these, it's going to seem a bit overwhelming, but there's really only like 4 things and maybe 2 bond angles you need to remember for the whole process. All right? And we can do this again and just say we pull off another one of those, and we've got a non-bonding pair, maybe non-bonding pair, and atom. And then that ends up linear. So it's time that we start naming these things, I guess. It wouldn't hurt, right? So what is the name of this particular structure here? Well, that's linear. It's a line. This structure right here, we have 3 things in one plane, so we call it trigonal planar. And then this one is, literally, if you take a look at this versus this, it is bent, all right? Sometimes you see angular or other names, but this is bent. And it's important that we take note, because there is another one that's going to be bent. This one's based on trigonal planar based bent. So you'll see me say that, trigonal planar based. And that gives us the bond angle right there. And then that would just be linear if we needed to draw it. As I'm sure the more I talk, the more overwhelmed you start to feel, I want to point out that one of the handouts that I've come up with has all these geometries and everything on it. And this is a pretty significant revision of many tables that I've seen online. So while I did use some of the pictures, this format and this setup is something I came up with along with some of the notations there. But take a look. We have number of things attached is what we're really talking about, and then linear, trigonal planar, and now we get to something that is a little bit different. If I have 4 things to attach around a central atom, you would think at first glance that they're going to be 90 degrees apart, right? Everybody draws a Lewis structure for methane like this or some variation. Nobody likes to do it like I always mess with people, which is, oh, put them right there, right? But this is my way of saying this isn't reality, okay? We can fake these structures looking correct by moving things around, knowing like this, knowing these are going to be 180 degrees apart, or knowing these are going to be 120 degrees apart. We can make the Lewis structure match the 3D structure. If I have these 3 balloons and I try and arrange them in some incredibly inconvenient way, they will naturally go to their lowest energy state, which is in one plane 120 degrees apart. All right, we didn't have to worry about that for something that's linear around a central atom, because if you said, oh, I've got 2 things in my hand as the central atom, no one would think that they're going off at an angle. Everyone would say, oh, the lowest energy state there would be 180 degrees apart. The limitations of Lewis structures become rather apparent as compared to 3D structures once you look at something like CH4. Looking at this picture, most people would say, oh, these electron pairs are uniformly distributed around the central atom. But the catch is they're uniformly distributed in 2 dimensions, and in 3 dimensions there's a little more space to be used. So if I take some balloons, and this is going to be super inconvenient, and set them up that way, you'll notice that they're planar, they're all in one plane, but they're in a higher energy state. And if I shake them a little bit, they don't end up like they were. They end up in this type of geometry right here, which is tetrahedral. Again, my hand in the center there will be the central atom, and then these might be the attached atoms, right? So once again, we look at that structure for CH4, and we say, oh, that's going to be 90 degrees apart. When in fact, in 3 dimensions, there's all kinds of extra space, and we can get things about 109.5 degrees apart. With that in mind, we need a new tool, and that new tool is going to have to be to represent things 3-dimensionally on a 2-dimensional surface. And luckily, this is not the first time anyone's had to do that. Artists have been using perspective for many years. The idea that as things are closer to the observer, they get larger, and things that are farther away from the observer, they appear smaller. So what we're going to do is start drawing triangles, and we'll use dotted lines for the things going in. And there's a couple different ways that they do this, but we'll just go with the simple thing. For things that are in the plane or on the plane, those we'll draw as we normally would. So in the case of this 4 things attached, we've got our central atom. One of the things attached is going to be there. One of the things attached is going to be there. We can have 3 of those 5 things, 5 total things, 4 attached things, in one plane. But then the last 2, we're going to have to utilize 3-dimensional space. So the way we show that in chemistry is a triangle for the thing that's coming out of the page and a dotted line for the thing that's going into the page. So when you see this, what you see is on the plane of the page, on the plane of the page, on the plane of the page, coming out of the page and going into the page. And that's what we saw with those balloons a moment ago. In this particular case, as I mentioned when I had the balloons in my hands, this is not 90 degrees like we would expect for this. It is around 109.5. And that makes sense because, according to VSEPR theory, we need things as far apart as possible. And 109.5 is farther apart than 90 degrees. So as we're looking at this right here, we expect around 109.5 degrees. That's a number that you're not just going to be able to pull out of thin air, most likely. So in terms of things that you probably have to straight up memorize, 109.5 is something you're not going to get away from. We can start then removing things from that, and we can see how they look. And I'm going to try this with modeling clay. I've done many, many different versions of modeling before with small styrofoam balls and toothpicks and actual modeling kits and everything else. Well, I don't have any of that at home, but I do have some modeling clay that I stole from my children's crafts box, along with some pipe cleaners that I stole from their crafts box as well. And so I set these up in very specific shapes to kind of give us an idea of how these things are going to work. And we're going to go somewhat slow-mo back through how we made that CH4. And I'm going to start with the wrong structure for that CH4, and then we're going to turn it into the right one. So as I was showing with the balloons and with our Lewis structure drawing, you expect something like this that has those 90 degrees apart, those hydrogens. In reality, all of this space on each side of the atom gets wasted then, or each side of the carbon atom, and it becomes energy efficient as these two squeeze. Then this one pops out of plane a little bit, this one pops out of plane a little bit, and then we get things that are, instead of 90 degrees apart, about 109.5, and it's uniform in all directions. And we'll write it down in a minute, but that's what's called a tetrahedral geometry. Now what happens, that's what we drew right here in fact. So if you look, this would be on the plane of the paper, this would be on the plane of the paper, and then this one is coming out of the plane of the paper, and this one's going into the plane of the paper. That's this one and this one. All right, so if we show that way. What happens then if instead of 4 attached atoms, I have a non-bonding pair? So if I remove this from here, you might say, oh, this is going to snap back and be trigonal planar, because trigonal planar is 3 things attached. But what we need to take into consideration is, in the case of something that was tetrahedral, we're going to have a non-bonding pair there that is left behind. So while we won't actually see anything, we're going to end up with something that is not planar. In this case, it is a pyramid. All right, so let's see if we can represent that on our page here. This we just said was tetrahedral. What happens then if I remove, for instance, this one? And I think that's an easy one for us to remove in this picture. We'll put a non-bonding pair right there. We've still got that atom coming out of the plane. We've still got the atom going into the plane. And we still have that atom on the plane. All right? So we have exactly what you see here, which is this atom going to our central atom, this atom coming out of the page, and this atom going into the page. And we do end up with a bond angle slightly less than 109.5 degrees. And I'm going to put that in there. And a lot of people ask, like when you're looking here, what does less than 120 mean? It means literally less than 120. No one's going to ask you to memorize exact bond angles, but you would be expected to know that a trigonal planar structure, when you have a non-bonding pair instead of an attached atom, that angle decreases. That non-bonding pair is repelling more, and so that angle gets squished a little bit. Maybe it's 118 or something, right? Or in this particular case, instead of 109.5 for something like NH3, maybe you end up with like 107. And then if we chop another one off, I think you'll recognize that, and you may know a bond angle for that as well. So let's grab our 3D model here, and we'll pull another one of these off. Okay, so I've now turned this into a non-bonding pair, and I now, according to this picture, have one going out and one going into the page. And a lot of times you'll see books drawing it like this, but I think that's kind of counterintuitive, because if you look, you've only got 2 things attached, and we can definitely fit all that in a plane if we keep track of our bond angles. So what happens then when we remove 2 of our attached atoms and replace them with 2 non-bonding pairs? That might look familiar to you. So those pink loops again are non-bonding pairs, and then the red ones are attached atoms. A classic example would be water, and I'm going to draw it not by removing this, but by shifting it a little bit in 3-dimensional space, so we're drawing it all in one page. We have a non-bonding pair and a non-bonding pair. Theoretically, that was a circle there, and that is this right here. Attached atom, non-bonding pair, non-bonding pair. I'm not going to show them, but I want you to realize that this is bent rather than linear, because we don't have nothing around our central atom. We have 2 non-bonding pairs which are repelling, and it pushes these things down out of plane. And our bond angle in this case ends up a little smaller than what we just saw, so still less than 109.5, And in this case, maybe like for water or something, around 105 degrees. So there are some names we want to get straight with this. This is tetrahedral. This is a triangle-based pyramid, so it happens to be called Trigonal Pyramidal. All right? And then this, if you look at it, looks strikingly like what we had here, where it was a linear one that got pushed by a non-bonding pair. In fact, this one got pushed even more by another non-bonding pair, and now we have two, and that's why that bond angle got even smaller. So you may see a name for this, bent or angular. I always use bent, because it literally looks bent. And this one's tetrahedral based. All right. I will just mention as a last thing to draw here, although it's not a real concern for us. All right, the marker I haven't used. You could also then pull the last thing off, right? And just have one attached atom with three non-bonding pairs, and those are still going to be 109.5 off of each other. So it would be something like this. And you might have, you know, there's your central atom, three non-bonding pairs, and then your attached atom. And then that would be linear. We don't have to write it. And there we go.